If you have ever tried to study chemistry by reading Chapter 1 front to back, you know the feeling of drowning in definitions. Hundreds of pages of dense text often obscure a handful of core concepts. We are going to bypass the bulk. Grab a single blank piece of paper and a pen. Over the next 5 minutes, we are going to extract every definition, law, and formula required for your exams and lock them onto this single page. By organizing raw data into a strict spatial framework, we turn passive reading into an active, functional tool. Start by drawing a bold cross right down the middle of your page, dividing it into 4 equal quadrants. Number them 1 through 4. Each box has a specific role. Box 1 is for basics, Box 2 holds the rules, 3 defines your particles, and 4 is dedicated to the math. In Quadrant 1, write the word matter. Below it, define its 2 required traits. It must occupy space, and it must have mass. Next, split the rest of this box into physical and chemical changes. The distinction is simple. Does the process result in a completely new substance? Write down these examples. If ice melts into water, the state changes, but it is still H2O. That is a physical change. But if iron develops rust, the chemical identity itself is altered. That is a chemical change. Distinguishing between a change in appearance and a change in identity ensures you are only applying chemical logic to actual chemical reactions. In Quadrant 2, we establish the metric foundation. List these 5 critical SI units: length in meters, mass in kilograms, time in seconds, temperature in Kelvin, and the amount of substance in moles. Below that table, we record the laws of chemical combination. First is the law of conservation of mass. Write 10 grams plus 5 grams equals 15 grams. This illustrates that mass is neither created nor destroyed during a reaction. It is simply redistributed. Second is the law of constant proportion. This states that a specific compound will always contain its constituent elements in a fixed ratio by mass. For example, water, H2O, always maintains a mass ratio of exactly 1 part hydrogen to 8 parts oxygen. This ratio remains constant regardless of the water's source. These laws provide the mathematical boundaries that govern how every reaction behaves in a lab. Moving to Quadrant 3, summarize Dalton's atomic theory. His central postulate is that matter is composed of indivisible atoms that cannot be created or destroyed. Next, we need to define the 3 types of particles you will work with: atoms, molecules, and ions. Use these shorthand descriptions. An atom is the smallest unit, a molecule is a group of atoms, and an ion is simply charged. Attach an example to each. Write H for a single atom, H2 for a molecule, and Na+ for a sodium ion. Clearly categorizing these particles at the start of a problem prevents errors when you begin calculating molar masses. Moving to Quadrant 4, we tackle the concepts that appear most frequently on exams. First is the mole concept. Write down Avogadro's number. 1 mole equals 6.022 times 10 to the 23rd power. This number allows us to bridge the gap between individual atoms and measurable grams. Underneath, define molar mass as the mass of 1 mole of a substance. Record 2 reference points. H2 is 2 grams per mole, and H2O is 18 grams per mole. Finally, we must distinguish between a molecular formula and an empirical formula. A molecular formula shows the actual number of atoms in a compound. For glucose, that is C6H12O6. The empirical formula is the simplest whole number ratio of those atoms. By dividing the subscripts in glucose by 6, we get the empirical result, CH2O. This ratio serves as the baseline for more complex calculations, providing the simplest mathematical identity of the substance you are analyzing. Stop writing and look at the page in front of you. You have successfully compressed an entire textbook chapter into a functional, single-page reference. Before starting a practice test, spend 30 seconds scanning this sheet to refresh the core rules in your mind. Academic preparation is most effective when you take scattered data and engineer it into a structured, actionable system.